When we last left off, we were discussing different types of chemical reactions. So now what I'm going to do is let's discuss a new class of chemical reaction known as the creatively named gas evolution reactions. As the name implies, they're reactions that generate gas. These can be redox reactions, such as, for example, a hydrogen displacement. Can be an acid-base reaction, as we've seen in reactions that generate ammonia or hydrogen sulfide, or it could be a decomposition reaction. So gas evolution reactions just describe any reaction that makes gas. This will be covered a lot more in the chapter on gases. Okay. So in the next example, we're going to look at this set of reactions and we're going to classify each reaction, and then we're going to write balanced chemical equations and net ionic equations. So let's do this first example together. So we have hydrogen sulfide reacting with oxygen gas to generate sulfur dioxide and water. So what type of reaction is this? If we have reaction with oxygen gas to generate water and other oxidized products, what do we call that reaction? If we're lighting hydrogen sulfide on fire, what do we call that process? What do we call that reaction? What do we call that reaction? What do we call that reaction? And don't be shy to type your responses in the chat or unmute. It is a redox, yes, that is one potential way of describing this reaction. But in terms of reaction with oxygen, this would be called a combustion reaction. So the key signpost is this oxygen gas. It's a sign we have a combustion reaction. So balancing this combustion reaction, first and foremost, we have an isolated pure element, so we can utilize half notation. So hydrogen's balanced. We have 2 hydrogens on each side. We have 1 sulfur on each side. We have 2 oxygens on the left. We have 2 oxygens plus 1 or 3 oxygens on the right. So I'm going to place a coefficient of 3 over 2. And then I'm going to multiply all of my coefficients by 2. This is known as the half notation shortcut, and it's invaluable for balancing combustion reactions. Perfect. So here's our balanced chemical equation, and this is a combustion reaction. Note, we don't have to necessarily write out an ionic equation because the molecular and ionic equations are the same in this case. Any questions? So let's do another example. Yes, we discussed combustion in, let me show you the page. So we discussed combustion on page 89. So combustion is a reaction where you have a compound containing carbon, hydrogen, and nitrogen reacting with oxygen gas to yield carbon dioxide, water, among other products. So let's look at this next example. So we have lithium sulfate and lead nitrate reacting to generate lead sulfate, solid, and lithium nitrate. So we're generating a solid insoluble ionic compound. So what do we call this kind of reaction? What do we call this kind of reaction? Where we're combining two solutions and generating an insoluble ionic compound. What do we call that kind of reaction? What would we call that reaction? Yes, it is a double displacement or an exchange reaction. What else? What specific type of exchange reaction is this? What do we call this insoluble solid? What do we call this insoluble solid? It's just a precipitation reaction. This insoluble solid is our precipitate. So this is a precipitation reaction. So then let's balance this equation. So the main feature of classifying different reactions is by virtue of classifying different reactions, we can more efficiently utilize shortcuts to balance these equations and write the net ionic equation. So looking at the following example, we have 2 lithiums, 1 sulfate, we have 1 lead and 2 nitrate on the left. We have 1 lead and 1 sulfate on the right, and then we have 1 lithium and 1 nitrate on the right. To balance lithium, 1 times 2 would give us 2. And now we also have 2 nitrate. So now our equation is balanced. Now we're going to write out our total ionic equation. So we dissociate all of our soluble ionic compounds, strong acids, and strong bases. So we keep lead sulfate together because it's insoluble. And now we break apart nitrate, lithium nitrate, into 2 lithium and 2 nitrate. Now we cancel our spectator ions. And as we discussed previously in earlier lectures, the net ionic equation for a precipitation reaction can often be simplified down to the combination of the 2 ions found in your precipitate. Does this example make sense to everyone so far? Okay, so let's now try to apply what we've learned, and I'd like you to look at the following 2 reactions. I'd like you to classify the following reactions and then write balanced chemical equations and net ionic equations for each reaction. And we'll discuss this first reaction 1 in about 3 to 4 minutes. Don't be shy to type in the chat what type of reaction do you think this is and what the net ionic equation would look like for each of these 2 reactions. So to answer the questions in the chat, yes, in precipitation reactions, we generally will have spectator ions. And the proposed classification for reaction 1 in this problem solving session is exactly right as far as I see in the chat. You could call it a double displacement. There's another name for this specific type of reaction that we've actually just talked about. So let's continue working on this problem and let's try to, yep, it's also a precipitation reaction, exactly right. Now let's try to write the net ionic equation and balanced chemical equation for this first reaction. And we'll discuss this example in about another minute and a half to 2 minutes. Okay, so let's discuss this first example. So looking first and foremost, we're going to check that our equation's balanced, which it is. We know that we're combining two solutions to generate a solid precipitate. We also see that there has been an exchange of cations. So we call this an exchange reaction and a precipitation reaction. So that in turn gives us, next, if we want to write out the net ionic equation, we break down each of our soluble ionic compounds into their component ions. Copper sulfide, we do not dissociate because it's an insoluble precipitate. Then we cross out our spectator ions. And that in turn gives us the following net ionic equation, which, as we discussed for most precipitation reactions, will just be the combination of ions. Yes, did someone have a question?
Yeah, Professor, in exams, are you going to ask us to name it as exchange or double replacement? Or
Either is fine. Either is fine.
and you're going to want us to classify it as a precipitate reaction?
Precipitation, yes.
Oh, okay.
Yeah.
Okay.
You'll have a list of options to choose from.
Okay.
So that way, if there are differences in like, for example, if I call it an exchange and it's a double displacement, those mean the same thing. So you'd select exchange.
But not all double displacements have a precipitation with it, right?
Yes, that's exactly right.
All right.
Precipitation is a specific class of exchange reaction where we generate an insoluble ionic compound.
Okay.
Exactly.
Cool. Thank you.
Perfect. So let's look at this second example. Let's first classify what type of reaction we have, and then let's try to write a net ionic equation. These are exactly the kind of examples you'll see on exam 3. So you want to be familiar with them. Yep, and the responses I see in the chat look great so far. And the proposed balanced and total ionic equation that I see looks perfect so far. Now all we have to do is cancel our spectators, and there we go. Wonderful, wonderful. So the equation's balanced. We have a total ionic equation. So sorry about that. Allow me to write out the instructor solution. So this is a displacement, formerly called a single displacement. If we want to be specific, it's a hydrogen displacement reaction. So with that established, first and foremost, we are going to balance all of our atoms. We have one hydrogen on the left, we have two hydrogens on the right. So we're going to add a coefficient of 2. Writing out our balanced equation now. We have the following balanced equation. We're now going to break up all of our soluble ionic compounds, strong acids, and strong bases. And that in turn gives us the following chemical reaction. Then we can cancel our spectator ions, and that in turn yields the following net ionic equation. And here we can clearly see the redox character of this reaction. Does this make sense to everyone so far? Does this make sense to everyone so far? It's amazing how just from a small number of pieces, we have the tools to predict the products of reactions, and we have the tools to write out equations fully after classifying each equation. So let's look at another example. So I'd like you to classify the following 2 reactions and balance their chemical equations. And again, I would recommend when you see an isolated pure element to try to utilize half notation. So we'll spend about 3 to 4 minutes on the first chemical equation. We'll classify the equation, then balance the equation and write the net ionic. This is exactly how you'd see these types of questions on the exam. So this is great practice. And the classifications that I see in the chat look great so far. Let's try to get some balanced equations in the chat or using the annotate feature, and then we'll discuss this example shortly. Yes, and the classification looks great so far for the first reaction. Yep. As the students in the chat have pointed out, the first reaction is in fact a combustion reaction. Would anyone in the class like to propose a balanced equation with the correct coefficients, either in the chat or using an annotate tool? If not, we'll discuss in about another minute. And the coefficients look good so far. And looking at the coefficient for oxygen, yep, that looks good. Perfect. Wonderful. Thank you again for providing input. Now let's come together to discuss, and I'll provide an instructor solution just so that way it exports in the notes. So this is in fact a combustion reaction. Other reasonable answers would be a redox reaction. Okay, so let's take a look at the following reaction and let's try to balance it. So we have 4 carbons and 6 hydrogens. We have 2 oxygens on the left. We have 1 carbon and 2 oxygens, 2 hydrogens and 1 oxygen on the right. So let's first balance carbon. So we need 1 times 4 to give us 4 carbons, and that gives us 8 oxygens as a result. Now to balance hydrogen, 2 times 3 would give us 6 hydrogens, and now we have 11 oxygens to work with. 2 oxygens times what would give us 11? Let's remember our half notation rule. We can use fractions, right? So what fraction are we going to guess? What fraction are we going to guess for oxygen's coefficient? What fraction are we going to guess for oxygen? (11/2), exactly right. Okay. However, we can't leave this chemical reaction as is. We have to multiply all of our coefficients by a common whole number, which is 2. So that in turn gives us 2 C4H6 gas plus 11 O2 gas leads to 8 CO2 gas plus 6 H2O gas. Okay, so now we have our balanced chemical equation established. And the balanced chemical equation is the exact same as our net ionic equation for this reaction. Okay, so let's look at one more chemical reaction. Let's look at reaction 6. Let's spend about 3 to 4 minutes classifying this reaction and balancing the chemical equation. And just think that if we're going from one compound to 2 or more compounds, what do we call this idea? So this reaction is quite infamous, as ammonium nitrate is a principal component of fertilizers. And well, if stored improperly, ammonium nitrate can decompose explosively, as shown in this reaction. So what type of reaction is shown here, where we're going from one compound to 2 or more compounds? Decomposition, exactly right. Okay, so let's try to get some balanced coefficients for this chemical equation, and then we'll discuss momentarily. Spend about another minute to ensure that we have a balanced chemical equation, and then we'll discuss. No problem at all, no problem at all. Okay, so let's discuss this example. So this is in fact a decomposition reaction, as we're going from one compound to 2 or more compounds. We have 2 nitrogens, 4 hydrogens, and 3 oxygens on the left. We have 2 nitrogen and 1 oxygen, and as well as 2 hydrogens and 1 oxygen on the right. So to balance hydrogen, 2 times what would give us 4 hydrogens? What coefficient do we need for water?
2.
2, yep, exactly. So that gives us 4 hydrogens and 2 oxygens. Wonderful. So we now have a complete balanced equation. Perfect, perfect. So let's talk next. We've talked a lot about solutions and chemistry involving solutions. So we have this wonderful chart that we prepared, remember when we discussed stoichiometry? The only thing new that we add is the fact that we can now go from the moles of a sample to the volume of a solution of that sample using molarity. That's the only thing we're adding in solution stoichiometry. So you can convert from volume in liters to moles using the molarity of the solution. In other words, moles is molarity times volume. Again, I can't stress this enough. The volume must be in liters. Okay, so we know how to do these kinds of calculations. So let's show a practical example of solution stoichiometry. We're instructed to transfer 3 grams of methyl bromide to 100 milliliters of 0.5 molar sodium iodide. This is known as the classic organic reaction of the Finkelstein reaction. Okay, we're asked how many grams of methyl iodide are expected. So just like before, the first thing we're going to do is we're going to figure out the moles of each of our reactants. So the moles of methyl bromide. So we have 3 grams of methyl bromide, and we know that in 1 mole of methyl bromide, we have how many grams? In 1 mole, we have how many grams? What is the molar mass of methyl bromide? (94.94). Yep, just to show everyone the logic, we take 12 for carbon plus 1 times 3 for hydrogen plus 79.9 for bromine. And that in turn gives us 94.94 gram per mole. Okay, so punching this molar mass calculation, we have 3 over 94.94. That gives us 0.0316 moles of methyl bromide. And if you're peering at this page of the notes, you're already seeing our good old friend, the ice table. So we have 100 milliliters of solution. We know that there are 10 to the negative third liter per mil. And we know we have 0.5 moles of sodium iodide in 1 liter. And that in turn gives us 1 moment. So we have 0.05 moles of sodium iodide. Okay, so now that we have the moles, we're going to write each of our reactants, and we're going to use the ice method. You may say, I don't like the ice method, I prefer the product method. That's okay. We can also do the product method, but I just want to refresh our skills with the ice method because it really is invaluable. So we write the initial moles that we calculated in each of our reactant columns. For our products, we write each of our products in, and then we put 0 initial moles for our products. Then in our ice table, we plug in the change coefficient. So what would the change coefficient be for methyl bromide? What times x? Is it 1x, 2x, 3x? What is our coefficient for methyl bromide? 1, yep. So minus 1x. For sodium iodide, it's minus 1x as well. Methyl iodide, it's plus x. Sodium bromide, it's plus x. So then, what we're going to do next is we're going to solve for x for each of our species. So x is 0.0316 over 1, which is 0.01316. This is for methyl bromide. And x is equal to 0.05 over 1 for sodium iodide. My question to all of you is, which of these values of X is smaller? Which reagent, which reactant is limiting? Which reactant is limiting? Methyl bromide. So what we're going to do is we're going to plug in the value of X is equal to 0.0316. So let's plug that in for X. So we have 0 moles of methyl bromide remaining. For our moles of sodium iodide remaining, we have 0.05 minus 0.0316. And that in turn gives us 0.0184. Okay, perfect. For our moles of product, we have 0.0316 plus 0.0316. So we have 0.0316 moles of sodium iodide produced. Allow me one moment just to reset OneNote. Sorry about that. When the file size gets a little bit large, sometimes OneNote likes to stutter and crash. Here we go. So we have 0.0316 moles of sodium iodide. So now all we have to do is, if we have our 0.0316 moles of sodium iodide, all we have to do is convert to the grams of sodium iodide. So if we have 0.316, oh, well, that is, whoops, sorry, that's not sodium iodide. One moment. So looking at our column, it's methyl iodide. Sorry about that. So we have 0.0316 moles of methyl iodide, and we need to convert to the grams of methyl iodide. And we can just execute on that mole to mass conversion using our molar mass. So how many grams of methyl iodide are present in 1 mole of methyl iodide? What is our mass to mole ratio? What is our mass to mole ratio? What is our molar mass of methyl iodide? 141.94. Okay, so we have 141.94 times 0.0316, and that in turn gives us 4.49 grams of methyl iodide. Perfect. Does this example make sense to everyone? The only thing that's new outside of the ICE table is the fact that to get to moles, we had to use our molarity. Everything else we've done before in the stoichiometry chapter. Does this example make sense? Is everyone comfortable with solution stoichiometry? I know it seems like a logical extension of stoichiometry, but I do want to make sure we practice it just so that way there are no surprises. Okay, so let's continue on now and let's look at the following problem-solving session. If you mix 30 milliliters of 0.4 molar potassium carbonate and 17 milliliters of 0.7 molar silver nitrate, I'm asking you how many grams of silver carbonate are expected to be produced from this reaction. And I provided you an ICE table to work through this problem. And I gave you a chemical equation, but I can't stress this enough. This is a common aspect of these types of problems. I'd like you to answer the question before we begin. Is this equation balanced? I can't stress that enough. Is this equation balanced? And let me change this to potassium nitrate. Is this equation balanced? It's not balanced. So you're going to need to balance it first by adding the following coefficients of 2 and 2. always check to make sure your equation's balanced. You can't do stoichiometry without a balanced chemical equation. Now, with the following balanced chemical equation, I'd like you to calculate the expected mass of silver carbonate product that you would get from this reaction. Yep, exactly right. And remember, just like as students in the chat are pointing out, make sure to convert your volume into liters. And we'll discuss this example in another approximately 2 to 3 minutes. And once you get to moles, you're home free. And we'll discuss this example in about another minute and a half. And if anyone would like to type in their proposed response for the mass of product silver carbonate generated, don't be shy to ask. Don't be shy to let us all know in the chat. And I'd be happy to provide feedback. Okay, so let's discuss this example. So first and foremost, let's calculate the moles of each of our chemical species. So the moles of potassium carbonate, we have 30.0 milliliters. we know that we have 10 to the negative third liter per mil, and we have 0.40 moles of potassium carbonate in 1 liter. So that in turn gives us 30 times 0.4 over 1,000, which gives us 0.012 moles of potassium carbonate. For our moles of silver nitrate, we have 17.0 mils times 10 to the negative third liter per mil times 0.70 moles of silver nitrate. So we have 17 times 0.7 over, and that gives us 0.0119 moles of silver nitrate. So now we fill in our ice table, keeping in mind our coefficients. Okay, so now we enter our moles. So for potassium carbonate, we have 0.012. For silver nitrate, we have 0.0119. Okay. Our change coefficient for potassium carbonate will be minus X. What is the change coefficient for silver nitrate? What is the change coefficient for silver nitrate? Two, yep, so minus 2X, okay. Silver carbonate is plus X, potassium nitrate is plus 2X. Okay, so now solving for X for potassium carbonate, we have 0.12 over 1. We have 0.012, that's for potassium carbonate. And X is equal to 0.0119 over 2 for silver nitrate, which in turn gives us an X of 0.00595. Okay, so which value of X is smaller? What reagent is limiting? Silver nitrate or potassium carbonate? Which reactant is limiting? Silver nitrate or potassium carbonate? Silver nitrate. So we're going to plug in the value of X for silver nitrate. So we have 0 moles of silver nitrate remaining. We have 0.00605 moles of potassium carbonate remaining. And then for silver carbonate, we have plus 0.00595, which gives us 0.00595 moles of silver carbonate. And now let's finish off this problem. So if we have 0.00595 moles of silver carbonate, my question to all of you is, in 1 mole of silver carbonate, whoops, I need to put that on the bottom. In 1 mole of silver carbonate, we have how many grams? What is the molar mass of our product, silver carbonate? What is the molar mass of our product, silver carbonate? Has a large molar mass of 275.75. So punching that into my calculator of 0.00595 times 275.75, which gives us 1.64 grams of silver carbonate. So really, once we get to moles, nothing's changed about these types of problems. Any questions on these examples?
Hey, Professor, if we
Yeah.
want to find the final moles for potassium carbonate
Yes.
through dimensional analysis, we would just figure out the moles for silver nitrate and then subtract that by the final moles of potassium carbonate.
If you wanted to figure out what?
The final moles of potassium carbonate.
Yes. So essentially, if you don't want to solve for, if you don't want to use the ice method, you'd take the moles of silver carbonate, you'd convert it, and
Sorry, you broke up. I couldn't hear you.
so you would take the moles of silver carbonate, convert it to the moles of potassium carbonate, and then subtract it from your initial moles of potassium carbonate.
Okay.
Okay.
Cool.
Does that make
Yeah.
sense?
Yeah. Thank you.
Perfect. So let's work on another example. So this time you can use any method, including the product method if you prefer. And given if you have a 2-gram sample of aluminum and you add it to 30 milliliters of 6 molar HCl, I'd like you to calculate the mass of hydrogen generated. Yep, this is a single displacement. And the trick now is to predict the product, making sure that you are respecting the overall charge balance of your products. And as this is a redox reaction, you could also use redox methods of balancing. So this problem's a little bit tricky in that you will have to predict the products and write the correct formulas of the products in order to balance this equation. So we know hydrogen gas is going to be generated, and I'd like you to try to figure out what the other product and the correct formula of the other product from this reaction. And we'll discuss the chemical equation that you need to complete this stoichiometry problem in about 2 to 2.5 minutes. And don't be shy to propose the chemical equation for this reaction in the chat. Okay, so let's talk about this example. So this is a displacement reaction where aluminum displaces hydrogen from hydrochloric acid. So we have aluminum 3 plus and Cl minus. We cross our charges, that gives us AlCl3, and hydrogen gas is our other product. So looking at our equation, what we're now going to do is we're going to balance this equation. So as looking at this equation, we have 3 chlorines on the right, so we need 3 chlorines on the left. So 1 times 3 would give us 3 chlorines. Now that we have 3 hydrogens on the left, if we have 2 hydrogens on the right, we need a coefficient of 3 over 2. Now to balance this equation, we multiply all of our coefficients by 2, and that gives us 2 aluminum solid plus 6 HCl aqueous leads to 2 aluminum chloride plus 3 H2. So now that we have the following equation, I'd like you to take your provided quantities of each reactant, and I'd like you to calculate the mass of hydrogen generated. So let's spend about another 4 to 5 minutes calculating the mass of hydrogen generated. And we'll discuss this example in another 3 to 4 minutes. Don't be shy to message me in the chat or via the annotate feature your proposed mass of hydrogen generated. And if you have any questions as you're working through the calculations on this problem, don't be shy to ask. And just as a reminder, make sure you convert your volume from milliliters to liters. Otherwise, you're going to get a very large number. and we'll discuss this example in another minute and a half. Okay, so let's discuss. So if we have 2 grams of aluminum, let's convert our grams of aluminum to moles of aluminum to moles of hydrogen to grams of hydrogen. When I say hydrogen in the context of a chemical reaction, I'm referring to H2. Okay, so 2 grams of aluminum, setting up my mole to mole conversion. In 1 mole of aluminum, I have how many grams? What is the mass, molar mass of aluminum? 27. Yep, so we 27 grams per mole of aluminum. Now looking at our equation, how many moles of hydrogen do we have per mole of aluminum?
Three to two.
Yep, exactly right, 3 to 2. And then we know that we have 2 grams of hydrogen and 1 mole of hydrogen. Now, punching this into our calculator, we have 2 over 27 times 3 over 2 times 2. And that in turn gives us 0.22 grams of hydrogen. Okay, let's do the same calculation for HCl. We have 30 milliliters of HCl. So we're going to go from 30 milliliters of HCl to the moles of HCl to the moles of hydrogen to the grams of hydrogen. Okay, we have 30.0 milliliters. We know that we have 10 to the negative third liter per mil. And we know that we have 6 moles of HCl per 1 liter. Where do we get that from? It's a 6 molar solution. Oops, sorry about that. So my question to all of you is, how many moles, looking at our chemical equation, how many moles of hydrogen do we make per mole of hydrochloric acid? What is our mole to mole ratio? What is our mole to mole ratio? Reading our coefficients.
3 to 6.
3 to 6, exactly right. Okay, and then finally we have 2 grams of hydrogen per 1 mole of hydrogen. So punching this into our calculator, that in turn gives us 30 times 6 over 2 times 2 over 1,000. That gives us 0.18 grams of hydrogen. So that's the actual mass of hydrogen generated. In other words, we can say that HCl is limiting. Does this example make sense to everyone? Everyone feeling comfortable so far with this idea of solution stoichiometry? Okay, so let's now do another example. This time, I'm going to be guiding you through this one. Because if you aren't careful, this example, although it looks very similar to an example that we've done before, Would someone like to comment on what's so special about this chemical equation? I'll give you a hint. There's something quite off with this chemical equation at first glance. What's special about this chemical equation? What type of reaction is this? And no, I did not make a typo on this equation. What type of reaction is this? It's a redox reaction. It's a redox reaction. Okay. So that is immediately a sign for concern. And that is part of the reason why we're missing one of our other products from this reaction. Okay, so we have to balance this using the redox method. So first things first, let's assign oxidation numbers. All of these oxidation numbers are standard following our rules. And now let's look at what's going on with oxygen. We are going from O2 to H2O. Let's assume acidic conditions for now. It doesn't actually affect the outcome of this process, but just as trivia, this reaction occurs if you try to store iodine or potassium iodide in acid in the presence of air. So you can also use this as an indicator for oxygen in air samples, as the iodide will turn to this dark brown iodine. Okay, so we're going from O2 to H2O. Okay, so we're going from 0 to -2. Is this equation balanced with respect to oxygen? Looking, we have 2 oxygens on the left, 1 oxygen on the right. So what coefficient do we need for water? What coefficient do we need for water? 2, yep. So that gives us 2 oxygens. Okay, now we have 2 times 2, we have 4 hydrogens. Okay, so how do we get 4 hydrogens on the left? What do we add to the left? How many H pluses do we need to add? 4, yep. Okay, and now if our difference in electrons is 2 minus 0, so we have -2 minus 0, so we have gained 2 electrons per oxygen atom, and we have 2 oxygen atoms. That gives us 4 electrons gained. So we put the 4 electrons also on the left-hand side. Now what we're going to do is we're going to look at potassium iodide and iodine. So I'm just going to separate it into the net ionic equation. So we have iodide going to iodine. And my question to all of you is, after just rewriting our oxidation numbers, is our equation balanced with respect to atoms? Do we have the same number of iodine atoms on each side of our equation? Do we have the same number of iodine atoms on each side of our equation? So we clearly have different number of iodine atoms on each side. We have 2 iodines on the right, we have 1 iodine on the left. 1 times 2 gives us 2. Okay, now we can count electrons fully. Our difference is 0 minus -1. So we have 1 electron. This is 1 electron lost per iodine atom. And we have 2 iodine atoms. So that gives us 2 electrons lost. Okay, so now that we have our equations, so we have 2 iodide leads to iodine plus 2 electron, and we have 4 electrons plus 4H plus O2 leads to 2H2O. What do I need to multiply my top equation by in order to have the same number of electrons on each side? 2, okay. So our 4 electrons cancel, and we're left with the following equation. 4 iodide plus 4H plus O2 plus 2I2 plus 2H2O. Okay, so we're finally done with that part. Now we can actually start solving the stoichiometry problem. Now we can actually start using the product method. So now that we have our balanced equation, let's look and let's identify our quantities. We have 10 grams of oxygen and 50 mils of 0.25 molar potassium iodide. Okay, so starting with 10 grams of oxygen. So we have 10 grams of oxygen. So we're going from the grams of oxygen to the moles of oxygen to the moles of iodine to the grams of iodine. Okay, so we know that in 1 mole of oxygen, we have 32 grams. How many moles of iodine do we have per mole of oxygen? How many moles of iodine do we have per mole of oxygen? Two to 1, that's exactly right. We have 2 moles of iodine generated per mole of oxygen that reacts. And how many grams of iodine do we have per mole of iodine? What is the molar mass of iodine? What is the molar mass of iodine? $254, yep. Okay, so let's punch this into our calculator. We have 10 over 32 times 2 times 254, which gives us 159 grams of iodine. Whew, that's a lot. Okay. Well, let's look at our other case. I'm pretty sure oxygen's in excess. We have 50 milliliters of 0.25 molar potassium iodide. So we're going to go from the milliliters of potassium iodide solution to the moles of potassium iodide, to the moles of iodine, to the grams of iodine. So we know that there are 10 to the negative third liter per mil. And just to check the molarity one last time, it's 0.25 molar. So we know we have 0.25 moles of iodide per one liter. And my question to all of you is, how many moles of iodine do we have and generate in this reaction per mole of iodide? What is our mole to mole ratio? What is our mole to mole ratio? Two to 4, exactly right. Okay, and then we know that we have 254 grams of iodine per mole of iodine. And that in turn, if we punch that into our calculator, gives us 50 times 0.25 over 2 times 254 over 1,000. That gives us 21.7 grams of iodine. And the least amount of product generated is the amount generated from our limiting reactant. So despite all the work to balance this redox equation, once we have our balanced equation, we've already done this kind of stoichiometry process before. In fact, we've demonstrated that in the earlier examples. So we're putting together balancing redox equations and reaction stoichiometry. Now, the key thing I want you to keep in mind here is that I'm not necessarily going to tell you that it's a redox reaction. You're going to have to look at the equation and be conscientious of whether the equation needs to be balanced using the atom counting method or using the electron counting method for redox reactions. Does that make sense to everyone?
Hey, Professor, I got a different number for that second iodine count.
Okay, let me check. 50 times 0.25 over 2 times 254 in my calculator. So we have 50 times 0.25 over 2 times 254 over 1,000. That gives us, 1.59 grams. Sorry about that. There must have been a missed decimal point in my calculator. Did that
And
match? Does that match?
even if they gave us the molarity for potassium iodine,
Yep.
we just use.
It's the same as iodide because it's a 1-to-1.
Okay, so
Yeah.
then like for that middle part where you have the molarity over liters,
Yeah.
we just that's when we use that the net ionic, right?
Yes,
On the step
exactly.
after.
Mm-hmm. Yep, exactly right.
Okay, cool. Thank
And
you.
just to note here, for potassium iodide, we have 1 mole of iodide per mole of potassium iodide. And I just shortcutted through that step just to save space. You do have to look at the formula to make that conversion, but since it's 1-to-1, I felt like including it would be a little excessive. But in later problems, this formula ratio may come into play. And we'll talk about that. And we actually may see an example of that later on.
So like if it were calcium iodide,
Then it would be 2-to-1. Yeah, exactly.
okay, and then that's when we would incorporate it into the
Yep,
whole.
exactly right.
All right, cool.
Mm-hmm. Any other questions on this example? This is about as difficult as these kinds of problems can get. It's a solution stoichiometry solution stoichiometry problem involving a redox reaction. Okay, so now that I showed you an example of this, let's take a look at the following problem. And I'd like you to calculate the mass of iron 3 plus generated when 15 grams of potassium chromate reacts with 25 milliliters of 0.45 molar iron 2 chloride. And I've given you the following net ionic equation that is unbalanced. So our first order of business is to balance this equation. Our second order of business is to then calculate the mass of product generated. So we'll take about 4 minutes and write out the balanced chemical equation, and we'll discuss the balanced chemical equation in about 4 minutes. Again, don't be shy to propose your balanced equation in the chat, or if you're feeling ambitious, you can even propose the mass of iron expected from this reaction. And just to make sure we're all on the same page, this is a redox reaction, so just be very conscientious of that. And we'll discuss in about 4 minutes. And if there are any questions, don't be shy to specify them in the chat. We'll discuss this example in about another 2.5 minutes. And we'll discuss this example in another minute. Okay, so let's discuss this example. So first and foremost, we're going to assign oxidation numbers in dichromate. So oxygen has an oxidation number of -2 for chromium. So for chromium's oxidation number, we have -2 times 7 minus the total charge of -2 over the number of chromium atoms, which is 2. That gives us an oxidation number of +6. Continuing on now, that in turn yields chromium 3+. In order to balance chromium, we have a coefficient of 2. And chromium is in the +3 oxidation state. Now that we have this established, we look and we count our atoms on each side. So we're going to assume, again, unless specified in the problem, we can assume acidic conditions. And in turn, that means if we have 7 oxygens on the left, we'd need to add how many water molecules on the right? How many water molecules do we need to add on the right? How many water molecules do we need to add to balance oxygen? And don't be shy to submit your proposed responses in the chat or verbally. 7, exactly right. We need 7 water molecules. That gives us 14 hydrogens and 7 oxygens. So then how many H pluses, how many hydrogens do we need to add to the left-hand side? 14, yep. Okay, perfect. Now in terms of electron counting, our difference. So we have 3 minus 6, so we have 3 electrons gained per chromium. So then we have 2 chromium atoms, so that gives us 6 electrons gained. Okay, so let's now continue on with this equation and let's look at iron. Iron's the easy one. We go from Fe2 plus to Fe3 plus. In other words, we went from +2 to +3. Our difference is 3 minus 2, which gives us 1 electron lost per iron times 1 iron. So that gives us 1 electron lost. Now that we have our number of electrons established for each of our redox reactions and we've balanced each of our redox half reactions, let's now focus on calculating and combining our redox reactions together in order to generate a balanced chemical equation. So in order to balance electrons, what should I multiply our top equation by? What should I multiply our top equation by in order to cancel our electrons? What should I multiply my top equation by to cancel electrons? Just to keep in mind that our bottom equation, we are gaining 6 electrons. So how many electrons does iron have to lose? 6. So then we're going to multiply the top equation by 6. And if we add our equations together, the electrons cancel. That gives us 14H plus Cr2O7 2 minus plus iron 2 plus. Allow me one moment. I'm noticing a bit of lag in OneNote. So allow me 1 second just to reset OneNote. Sorry about that small delay. So now when we combine our equations together, that in turn gives us the following balanced redox reaction. So we have 6 iron 2 plus 14H plus dichromate leads us to 6 iron 3 plus 2 chromium 3 plus 7 H2O. So here's our following balanced equation. Now let's rewrite our balanced equation and let's use our balanced redox reaction in order to calculate the expected mass of iron 3 plus generated from this reaction. So here's our complete balanced chemical equation. And now let's use the chemical equation and our given amounts of each starting material to calculate the theoretical yield of iron 3 plus. So we'll work through this example and then we'll talk about this example in about another 4 minutes. and we'll discuss this example in another 3 to 4 minutes. And don't be shy to message in the chat your proposed yield for the mass of iron generated from this reaction. And we'll discuss this example in another minute and a half. Okay, so let's discuss this example. So first and foremost, we're going to convert our grams of potassium chromate into the moles of potassium chromate into the moles of, potassium dichromate into the moles of dichromate into the moles of iron 3 plus into the grams of iron 3 plus. So if we have 15.0 grams of potassium dichromate in 1 mole of potassium dichromate, we have how many grams? What is our molar mass of potassium dichromate? What is the molar mass of potassium dichromate? (294.14). Perfect. And we know that we have 1 mole of dichromate for every 1 mole of potassium dichromate. And now how many moles of iron do I have per mole of dichromate? What is our mole to mole ratio? What is our mole to mole ratio? Six to one, exact. Yes, 6 to 1. We have 6 moles of iron for every 1 mole of dichromate. Perfect. And now looking at our mole to mole ratio, let's convert our moles of iron 3 plus to the grams of iron. And how many grams of iron are present in 1 mole of iron? How many grams of iron are present in 1 mole of iron? What is the molar mass of What is the molar mass of iron? Would someone like to comment in the chat? What is the molar mass of iron? 55.85. Yep, very good. So let's punch this all into our calculator. So we have 15 over 294.14 times 6 times 55.85. That gives us 17.1 grams of iron. Okay, now let's do this exact same calculation for iron 2+. So if we're going to start from the milliliters of iron 2 chloride. So we have 25 milliliters of iron 2 chloride. We're going to go to the moles of iron 2 chloride, then to the moles of iron 2, then to the moles of iron 3+, and then to the grams of iron 3+. Okay, so we have 25 milliliters. We know that there are 10 to the negative third liter per mil. Additionally, whoops, one moment. We know that we have 25 milliliters of 0.45 molar iron 2 chloride. So we have 0.45 moles of iron 2 chloride per every 1 liter. We know we have 1 mole of iron 2+ per mole of iron 2 chloride. And now how many moles of iron 3+ do we have per mole of iron 2+? What is our mole to mole ratio? What is our mole to mole ratio? 6 to 6? Yep. Okay. And then our molar mass, just like before, of iron is 55.85 grams of iron in every 1 mole of iron. And that in turn gives us 25 times 0.45 times 55.85 over 1,000. That gives us 0.628 grams of iron 3+. So this is the actual mass of iron 3+ generated. Does this example make sense to everyone? Once you have your balanced redox reaction, these problems just simplify into a stoichiometry problem. So let's keep going now. So let's do a guided example where we utilize some additional aspects of of solution stoichiometry. So first and foremost, we're asked how many grams of precipitate forms when 2.64 liters of 1.2 molar sodium phosphate is reacted with 5.4 liters of 0.45 molar calcium chloride. Okay, so first things first, I'm going to write out my equation. So sodium phosphate, I have sodium plus, phosphate is PO4 3-. We cross our charges. That gives us Na3PO4. Calcium chloride, we have calcium 2+ and chloride is Cl-. We cross our charges. That gives us CaCl2. Both of these compounds are aqueous. Now, if we want to predict the product of a precipitation reaction, we attempt to exchange our cations, and we write the formulas of our new exchange products. So if we have calcium 2 plus and phosphate, which is PO4 3 minus, that gives us calcium 2 with 3 phosphates. And then for our second and final product, we have sodium plus and Cl minus. We cross our charges, that gives us NaCl. Calcium phosphate is a solid, sodium chloride is aqueous. This is using our solubility rules.
Isn't it calcium 3?
Oh, yep. Calcium 3, phosphate 2. Yep.
Perfect.
So now looking at the following equation, I'd like you to take a moment and ask yourself, is this equation balanced? Is this equation balanced? As we can clearly see, this equation is not balanced. So we're going to utilize the cross method to balance our coefficients. So first and foremost, we are going to balance phosphate, as we have 2 phosphates on the right. We're going to put a 2 in front of sodium phosphate. As we have 3 calciums on the right, we're going to put a 3 in front of calcium chloride, and then a 6 in front of sodium chloride to balance out our sodium and chloride ions. Now that we have a balanced equation, we can execute on solution stoichiometry. Okay, so we're combining 2.64 liters. So we're starting with 2.64 liters. We're going to go to the moles of sodium phosphate. Then we're going to go to the moles of calcium phosphate. And then we'll go to the grams of calcium phosphate. Okay, so let's execute on that. So we have 2.64 liters. And then looking up our molarity, oops, one moment. Let's look up the molarity of our compound. We have 1.2 moles of sodium phosphate per every 1 liter. Okay, and we know that we have 1 mole of calcium phosphate per every 2 moles of sodium phosphate. And how many grams of calcium phosphate? How many grams of calcium phosphate do we have in 1 mole? What is our molar mass of calcium phosphate? What is the molar mass of calcium phosphate? What is the molar mass of calcium phosphate? Just to make sure everyone's comfortable calculating molar masses, what is the molar mass of calcium phosphate? So punching the molar mass into our calculator for calcium phosphate, the molar mass of calcium phosphate one moment. The molar mass of calcium phosphate is 310 gram per mole. So punching this entire line item calculation into our calculator, we'll have 2.64 times 1.2 over 2 times 310, which gives us 491 grams of calcium phosphate, which is Ca3PO42. Let's do another calculation, this time looking at the yield from calcium chloride. So we're starting with 5.4. Let me just check. 5.4 liters. We're going to the moles of calcium chloride, then to the moles of calcium phosphate, and then to the grams of calcium phosphate. So we have 5.4 liters times 0.45 moles of calcium chloride, just to check that we have that plugged in right. Yep, 0.45 moles of calcium chloride per 1 liter. Now my question is, how many moles of calcium phosphate do we get per mole of calcium chloride? What is our mole to mole ratio? Let's look at our balanced equation. What is our mole to mole ratio of calcium phosphate to calcium chloride? It's 1 to 3. Okay, and we know that we have 310 grams of calcium phosphate per 1 mole of calcium phosphate. And that in turn gives us, so we have 5.4 times 0.45 over 3 times 310. That gives us 251.1 grams of calcium phosphate expected. Okay, perfect. So we finished the first portion of this problem. Let's now take a moment. So if we have, so let's write out our balanced chemical equation once again. And let's write out that we obtained 251.1 grams of calcium phosphate. Okay, and now to continue on this problem, we're asked to calculate the concentration. We're asked to calculate the concentration of calcium 2+ in solution at the end of the reaction. Okay, so calcium chloride is the only source of soluble calcium. So we're going to go from the liters of calcium chloride to the moles of calcium chloride to the moles of calcium chloride at the end of the reaction, then to the moles of calcium. Okay, so to execute on this, let's look at our initial moles. So we have 5.4 liters times 0.45 moles of calcium chloride per every 1 liter. And that in turn gives us 5.4 minus 0.45. That gives us 4.95 moles of calcium chloride. Okay, we're now going to take our 4.95 moles of calcium chloride and we're going to subtract the moles of calcium chloride required to make our product. So we're going to convert the grams of calcium phosphate into the moles of calcium chloride. So we know in 1 mole of calcium phosphate that we have 310 grams, and that we know that we have 3 moles of calcium chloride per every 1 mole of calcium phosphate. So punching this into our calculator, just like we calculated the amount of excess reactant remaining, that's exactly what we're doing here. 251.1 over 310 times 3 minus 4.95. And that gives us 2.52 moles of calcium chloride in excess. We know that there's 1 mole, one moment. Give me 1 second just to reset OneNote. So continuing on just where we left off. So we know that we have 1 mole of calcium 2+ per every 1 mole of calcium chloride. So that gives us 2.52 moles of calcium 2+. Now if molarity is equal to moles over volume, we'll need to figure out the total volume. And the V total is just V1 plus V2. So looking at our problem, we're just going to add the volume of each solution, which is 2.64 over 5.4. So we have 2.64 plus 5.4. That in turn gives us a total volume of 8.04 liters. So then to finish off this problem, the molarity of calcium is equal, the molarity of calcium in this case is equal to 2.52 moles of calcium 2+. Over 8.04 liters, which gives us a final molarity of 2.52 over 8.04, which gives us a molarity of 0.313 molar calcium 2+. Okay, so now looking at this problem, if we're asked to calculate the concentration of phosphate ion, this one we don't have to do as much calculations because we want to figure out the concentration of phosphate ion. We know that sodium phosphate is limiting. So the concentration of phosphate will be about 0. There won't be a very large amount of phosphate ion remaining in our solution. And that's because sodium phosphate is our limiting reagent and it's consumed first. Does this example make sense to everyone? Does the idea behind this example make sense? The only thing new is that now instead of calculating the mass of excess reactant, we calculated the moles of excess reactant and used the total volume to calculate the final molarity. Does this example make sense? Any questions on this example?
I'm still confused on when you did the 4.5 moles of calcium chloride.
Yeah.
Why couldn't you just go from the 251 grams of calcium phosphate?
Because we're trying to calculate the amount of calcium remaining in solution. Calcium. So as a result, if we just started with the 251, this gives us from converting from the moles of calcium phosphate to moles of calcium chloride, gives us the moles of calcium chloride that reacts. But when calcium chloride reacts, the calcium isn't in solution anymore, right? So we want to figure out from the amount that we started with, how much calcium chloride is left over. That's why we subtract the amount of calcium chloride that reacts based on the mass of our limiting reactant. Oh, sorry, based on the mass of the product that we make.
Okay, so then if we would have just done that 251, it was just what's in the product, right?
Yes, yes.
And we want to find out the total. Okay.
We want to find out the amount that's left over after the reaction is complete.
Okay.
So we start with 4.95, and this number is how much calcium chloride we use up in our reaction. That calcium is no longer in solution. It's locked into calcium phosphate.
Okay, that makes sense. Thank you.
Perfect. So let's try to apply what we've learned to the following example. So in this case, sodium sulfide reacts with copper 2 nitrate to give a precipitate. And if you mix 200 milliliters of 0.5 molar sodium sulfide with 50 milliliters of 1 molar copper nitrate, I'd like you to calculate the mass of the precipitate generated. But first and foremost, we need a balanced equation. So let's take about 3 minutes and let's try to write a balanced chemical equation for the following reaction. And we'll discuss the balanced chemical equation in about another minute and a half. Okay, so let's discuss sodium sulfide. So crossing sodium plus and S2 minus, that gives us Na2S aqueous sodium sulfide. Copper 2 nitrate, we have copper 2 plus and NO3 minus. We cross our charges, that gives us CuNO3 2. If we're predicting the product, we swap our two cations, and that in turn gives us copper 2 plus crossed with S2 minus. which is copper sulfide, and sodium plus and NO3 minus, which when we cross our charges gives us sodium nitrate. Sodium nitrate is aqueous. What about copper sulfide? What is the state symbol for copper 2 sulfide? What is the state symbol for copper 2 sulfide? Solid, it's a precipitate. Now we just have to balance the equation. We have 2 sodiums on the left, so we need 2 sodium nitrate on the right. Now, given that we know the initial quantities of each of our reactants, I'd like you to calculate the mass of precipitate generated in this reaction. So let's take about 3 to 4 minutes to calculate the mass of precipitate generated from this reaction. And we'll discuss this example in about 3 minutes. And don't be shy to message your proposed response for the mass of copper sulfide generated from this reaction. And we'll discuss in about another minute and a half. Okay, so let's discuss this example. So we're going to use the product method. So we're going to convert from the milliliters. Let's start with sodium sulfide. We're going to convert from the milliliters of sodium sulfide to the moles of sodium sulfide, to the moles of copper 2 sulfide, to the grams of copper 2 sulfide. So if we have 200 milliliters of solution, we know that there are 10 to the negative third liter per mil. We also know that we have 0.5 moles of sodium sulfide per every 1 liter. And now my question to all of you is, how many moles of copper sulfide do we make per mole of sodium sulfide? What is our mole to mole ratio? What is our mole to mole ratio? One to one, exactly right. Now my question is, how many grams of copper sulfide do I have in 1 mole of copper sulfide? $159 grams per mole, that's exactly right. Let's now punch this into our calculator. So to calculate the expected mass, we get 15.9 grams of copper sulfide. Let's repeat the same calculation for copper nitrate. So we're going to go from milliliters of copper nitrate to moles of copper nitrate to moles of copper sulfide to grams of copper sulfide. So that in turn gives us, we have 50 milliliters. We know that we have 10 to the negative third liter per mil, and we have 1 mole of copper nitrate per 1 liter. And we know that we have 1 mole of copper sulfide per every 1 mole of copper nitrate, and 159 grams of copper sulfide per 1 mole of copper sulfide. So punching this into our calculator, that in turn gives us 50 over 1,000 times 159. That in turn gives us 7.95 grams of copper sulfide. And there was a calculation error for the molar mass that was provided in the chat. Let's redo these calculations with the correct molar mass of 95.6. Let's punch that into our calculator. So we have 200 over 1,000 times 0.5 times 95.6. So that gives us 9.56 grams of copper sulfide. Then for our second example, we have 50 over 1,000 times 100. So we have 50 over 1,000 times 95.6, which gives us 4.78 grams of copper sulfide. And since the smallest mass is generated by reaction of copper nitrate is our limiting reactant. So now what we're going to do is, given that we have 4.78 grams of copper sulfide formed, we're going to calculate next the concentration. So looking at this problem, we're next asked to calculate the concentration of nitrate in the solution. So we want to figure out the concentration of nitrate in the solution and the concentration of sodium in the solution. Keeping in mind that we have combined, reading from our problem, 200 milliliters of 0.5 molar sodium sulfide and 50 milliliters of 1 molar copper nitrate. So let's take another 2 to 3 minutes and let's calculate the final concentration of nitrate and sodium in this reaction. Keeping in mind, if you pay special attention to this chemical equation, let's try to figure out whether sodium and nitrate change over the course of the reaction or if they are spectators. So let's spend about 3 minutes on the second part of this problem and we'll discuss momentarily. And don't be shy to message your proposed response for the final concentration of nitrate and sodium plus in the solution at the end of the reaction. And we'll discuss in another 2 minutes. Okay, so let's now discuss. So if we think about this equation in detail, are nitrate and sodium, are they changing in concentration or are these spectator ions? Are nitrate and sodium changing in concentration, or are they spectator ions? If we just think about this idea, we can figure out a very quick way to solve this problem. So do nitrate and sodium plus actually react? Do they actually change in this reaction? What does everyone think? Do nitrate and sodium actually change? No, these two ions are spectators. So as a result, we can treat it just like we can use our dilution equation. So we know M1V1 is equal to M2V2, where V2 is equal to 200 plus 50 milliliters, which gives us 250 milliliters. So for the concentration of nitrate, we know that we have 1 mole of copper nitrate per 1 liter. We know that we have 2 moles of nitrate per every 1 mole of copper nitrate. And then looking at our ratio of volumes, we know that M2 is equal to M1 times V1 over V2. So then for our initial volume for copper nitrate, we have 50 milliliters. And for our final volume, we have 250 milliliters. So at the end of our calculation, we get a final concentration of nitrate of, punching it into our calculator, get a final concentration of 0.4 molar. Let's repeat the same calculation for sodium plus. So we have 0.5 moles of sodium sulfide per 1 liter. We know that we have 2 moles of sodium plus per mole of sodium sulfide. And we know that we have 200 milliliters initially over our final volume of 250 milliliters. And that gives us our final concentration of sodium as 0.8 molar. So we don't even have to use necessarily an ice table or the excess reactant method, because these two ions are spectator ions. Does this idea make sense to everyone so far? Any questions on this example? So that'll be the end of the lecture for today. We'll finish off this chapter next class session.